Jack, Eugene, Jesse, and Molly, and I'm Steve myself. We created a tool to help folks in the developing nations monitor their own lung function, because in the developing world there's a lot of problems with air pollution, from industrial smoke, car outputs, as well as poor air quality measures. And in fact, one of the more infamous sort of problems is in China, where there's so much smog that people have to wear air masks just to go outside. And I myself also experienced this when I was growing up. I also had a lot of smog where I lived, and we couldn't even go outside because the rain was too slimy or the sky was too brown and it was hard to breathe. This is not just restricted to China itself. In other countries such as Cairo, Egypt, Cairo, the city in Egypt, and the Middle East, as well as other developing nations, there's a lot of air pollution. And this can cause a lot of lung problems, such as chronic obstructive pulmonary disease, a lot of other obstructive diseases such as asthma, as well as other restrictive diseases as well. So we thought that we should address this problem because, according to the World Health Organization, these are the top leading causes of death around 2012. And 3 of these causes are lung problems: lower respiratory infections, COPD stands for chronic obstructive pulmonary diseases, and lung cancer as well. And these are problems in developing nations, particularly China. And funny enough, China is not even the top countries with the most air pollution. Areas like Mongolia, Botswana, Pakistan, Saudi Arabia, Egypt, etc., the Middle East, have a lot of problems with large particulate matter. So we looked at things that we could do in terms of how to address this problem, what kind of needs are out there. And we looked at the existing solutions, such as tools that are used for monitoring asthma, peak flow meters. And we also looked at spirometers as well, which are used in hospitals, as well as diffusion lung capacity tests, which are also used in hospitals, as well as pulmonary clinics. The problem with these peak flow meters, spirometry, and DLCO, the diffusion lung capacity tests, is that peak flow meters themselves are not very sensitive, they're not very precise. In fact, if you measure it twice, you might get a different reading each time. Spirometers can be very expensive. They can go upwards of $2,000, and some equipment can go to the tens of thousands of dollars range. And some of this equipment is also in office only, and they're not connected to any sort of computers that can read sensitive data. So we crafted a project that would address these problems: a large volume of particulate matter, it's difficult to quantify and support respiratory function, and the high cost of existing solutions. So some of the key metrics that we try to go by are making a project that's effective, robust, and affordable. So when we looked at all the criteria that we wanted to create this project with, we wanted it to be something that was low power, low maintenance, portable, inexpensive, simple to use, accurate, reusable, and modular and robust. So our team actually did a lot of research into anemometers, how to measure airflow, and they came up with 3 different technologies that they looked at: mechanical sort of sensors, as well as thermal sensors, and electronic sensors. And of those 3 different methods, they found that electronic sensors were the ones that fulfilled all these criteria. So they created something that used electronic sensors, and this was the solution that our team came up with. This is actually a device that where the top was taken off, but you can see the internals. And we call this Respire. And this particular solution is great because it's actually cheaper to create. It's actually more portable so that people can take it to go with them. And it's also something that can potentially synchronize with computers, smartphone applications, so that it can increase care in patients and increase compliance for medication adherence purposes. So the project itself, again, is portable. It helps screen lung function. It's inexpensive, and it's something that we wanted to target towards third world countries with severe air pollution. How would you use this? How would you use the device? So let's say you're in Mongolia and there's a lot of air pollution. Mongolia is at the top, as you saw, in terms of air pollution, particulate matter. People have to wear air masks. So if you're one of these folks, you can take this device in your house and blow into Inspire, and then Inspire itself can give you feedback through some simple LED lights that tell you whether you should see a doctor or whether you're progressing in terms of your lung abilities, lung function. And it can show data on an application in future iterations. That way, the doctor can potentially conduct interventions such as smoking cessation, air filters, or providing medications. So I'm actually going to pass this over to the engineering team. They did the bulk of the work. Ingrid programmed the sensor as well as crafted it along with Charlie and Jesse. So I'm going to pass this off to him.
Alright, so this is one of our prototypes. So you can see there's 3 LEDs. The 3 LEDs represent the severity of your condition that we're trying to screen. And we have the sensor on the left, which is that big tape-looking thing, which senses your airflow and then correlates that using the circuit on the right, the Arduino, to figure out how your lungs are doing and to give you an indication on those 3 simple LEDs. Yeah, so this is a demonstration of our prototype. So with low forces, you can see it turns the yellow one on, which indicates, in this case, that your lungs aren't functioning well. With high stress cases, or afflicted, you see the white LED turned on, which is showing that your breathing is very intense. Next slide, please. So this is how it works when you actually blow on it. It was a pretty good run, yeah. So the final goal of our project was to actually put this into a device that was isolated from any sort of dust and dirt. So obviously this open enclosure is not going to work. And to make it a little bit simpler, so instead of using 3 LEDs, we just use 1 LED that can generate all the 3 colors and all the other colors that we needed. Next slide, please. Okay, so I'll pass this on to our other teammate who did a lot of the mechanical work.
Thanks. Okay, hi, I'm Jesse. I worked a lot on the 3D printing. So essentially I was just creating a case that would house the Arduino board as well as the sensor, the tubes that house the sensor, the piezo sensor that is collecting the exhaled air. And the exhaled air causes the piezo sensor to deflect, and those changes in deflection correlate with how strong your exhaled air and therefore correlates with some of the physiology and your lung functioning. So in the 3D modeling case, essentially just had a clamshell case, top and bottom lid. The bottom was housing the Arduino board, and you can see in the mock there the board there, as well as the tube and the piezo sensor that's housed in the tubing. And I'm going to pass this off to Steve to talk about our modeling.
Okay, hi everybody, I'm Molly. So you might be asking yourself why we manufacture this at such a lower cost. And part of that is that we use cheaper materials at our percent cost. And you see our estimated after mass manufacturing is almost half the cost. Also, we're advertising this not as an evaluation tool, but as a patient self-monitoring tool. So we don't have to go through the FDA very expensive regulations. If you look at some of our competitors, it can go up to $2,000, $1,200 for some of the cheapest available options for people. And then if we look at our needs analysis, these are all the areas that we're trying to target, and this is how we met those needs. Some of the most notable ones is that it's much more affordable, and it's reusable, disposable, and patients can have a self-monitoring in their home. This will help them see, like, okay, so the doctor had diagnosed me with this, I'm doing this to address these needs, is it actually working over a long period of time? So, I'm going to send it to Steve.
So we only have 10 seconds left to talk. So some of our users, particularly the insurance companies, government, as well as air filter companies, doctors, patients, and parents. We're going to skip over the slide as well. Some of the future directions that we can take with this product include more rigorous monitoring by crafting workflows that physicians and other nonprofit organizations can use. We can perform more rigorous lung tests. We can also shrink this down to less than a quarter of the size, because this is just a rough prototype that our team created. We can also potentially hook this up to a smartphone data display, add-on applications, with the integration, as well as for pediatrics patients, for kids who need to take their asthma medications, added to fun things like toys, kazoos, instruments, to make it more of a game. So that's our team: Charlie, Jesse, Indrajit, Molly, Steve, Berkeley, Zach from Camp Peter, and this is Respire. So we just wanted to open up to any questions that anyone has for us.
So we've got about 4 minutes for questions. Anything from our judges, or I can bring the mic back.
Yes, sir.
My question is, so if in hospitals it's more of a mechanical device that you could make where it's simply, you're blowing and there's a mechanical scale on the top. How is this kind of, why deviate from that, which seems to be kind of a little bit cheaper and actually fewer moving parts without electronics?
Right, so I think it sounded like the question was hospitals already have devices like this that have scales at the
They're
top.
purely mechanical, and since you blow and this part moves and the top part is a needle, it gives you some indication of how hard you're blowing.
Right. So that's a peak flow meter. So peak flow meters are commonly used by primary care physicians, and that's very insensitive. You can easily cheat that device. If you hold the button on the back of it, you can blow the top part of the mark. However, that is very low in sensitivity, and many of the pulmonologists we've been speaking to said that that technology will probably not be in existence a couple of years down the line. They no longer prescribe that actually. And so this technology, spirometry, accurately measures the lung function, such as gathering measurements of lung capacity, full forced expiratory volume, as well as the total lung capacity in your lungs, rather than just the peak flow, which is the maximum peak that you can expire your breath.
To support that as well, this has also meant that people can take this and have in their home, so they don't necessarily need to go to the doctor to get that information.
I just wonder, because part of the reason that that instrument is insensitive is the patient using it incorrectly. And if you actually use it well without cheating, actually, in my experience, is used fairly frequently. The patient use issues would probably be the same with an electronic meter. I would assume you still have to seal your lips around it. I just question the complexity. That's it.
That might be the one problem, but I think the advantage of our tools is those simple machines, they can only tell you one thing, and then they can't tell you much else. For ours, we can do all sorts of processing to make that you get more accurate and to help you log in onto your computer and all sorts of other things.
Where we get a lot more metrics, including volume versus rate chart that is important to physicians, whereas just a peak flow meter just gives you the maximum.
So you could get a whole
So we take
out of
the
that.
entire graph over a period of time, and we can actually collect important information for the physician.
So you want to give some other posts? Yes.
Yeah, have people validated how accurate you can get these measurements from simple piezo element?
So right now, I guess we can talk about that.
The case element itself, I think, is not accurate. That's because it's just a prototype. What we're actually planning, we looked up, the accuracy is basically based on how loud the pressure the air that's going through, and we see through other technologies that we could make it very accurate, like as accurate as
So my question is, what is the right sensor to have in your
So looking at all the
trade-offs and everything, we chose I think a resistant pressure sensor to be the best.
And the current spirometers, like we saw the spirometers that are for thousands of dollars, they also use electron sensor similar to ours.
They use pressure transducers that use a reluctance-based sensor. So they measure correctly.
So in a follow-up to that question, when you're comparing the cost to the spirometer, you're saying that is that in thousands of dollars, at least partially because of the FDA regulation. Aside from that, is there a difference in some other differences that would give rise to this difference in cost? Because I think if you do this in the US, you would need FDA approval as well, so you have to account for that in this cost. So are there some fundamental differences other than regulatory that account for that?
Right, so spirometers are commonly used only in hospital settings. And so there's a reimbursement code that's associated with that, with HCPCS codes and CPT codes. And so I think a lot of medical devices are value-based rather than just, I guess, cost-based. So that's probably what accounts for that. And then the competitive landscape for that is that many of these companies are selling them already successfully for thousands of dollars. So why change? But we want to create a low-cost solution.
But if there's no technical difference in the device, then they can just come in and swap here, right? If they're selling you for a certain price, because they can, but if you're saying that's actually the reason they can just come in, sell their device for much less.
I think the technical difference is also kind of tied to the portability. Portability allows for access into areas, for example, clinics that are farther, clinics that are in rural areas, or people in people's homes. So instead of having a spirometer that's at a clinic, that a patient would have to travel perhaps many miles to the clinic to access this. Ours has the advantage of being portable and being individualized for each patient.